Hi guys. Today we're going to look at another application of the exponential function, and we are going to look at carbon dating, or even less specific than that, just decay, radioactive decay. But probably the biggest application it has is with carbon dating. So what we look at is going to be pretty familiar, to what we have been doing. And we've changed a couple of the letters just to match some equations that I have. So it is similar to population growth, but this is just radioactive decay is one way to look at it. And we use N of T equals N naught E to the KT. Okay, so notice it's the same thing as population growth. We just replaced the P of T with the N and the P naught with the N naught. So N of T is the amount of substance that is left after a certain amount of time. Okay, so we will be dealing mainly with percentages, and we'll talk about that in a minute, but it could also be in kilograms or grams, milliliters. This can also be used with medicine, like how much medicine is left in your body at a certain amount of time. Okay, medicines do have half-lives. Some of the dye they use, things like that. Okay, and that's why you're not supposed to take a certain amount of medicines until a certain time later. Okay, but anyways, we're going to be looking at this with elements and such. N naught's the original amount of your substance. K is going to be your growth rate, and it should be a negative when we have decay. Okay, so keep that in mind. So yes, it's called a growth rate, but we're going to use it with the decay, which will make it negative. And then E is that 2.72 that's in your calculator, and then T is time. Now, unlike population and our compound interest, we are allowed to use time not only in years. Okay, so some things have half-lives of years, some have half-lives of days. Medicine, some of them have half-lives of minutes or hours. Okay, so time here can be different than years. Okay, so this equation is what we'll be using, but more than likely it'll be easier if we use a revised equation, and that is where we bring the N naught over to the other side by dividing. And so if we take the amount that's left over the original amount, that is a percentage as a decimal. So this is more useful to us. We don't have to know how much exactly we started with. Okay, so although we'll start with that original equation, we will be using the modified equation. Okay, so let's look at example 1. And this asks us to find the exponential decay function, so the equation, for the amount of phosphorus 32 that remains after T days. Okay, the additional information they give us is that it has a half-life of 14 days. Okay, so what does a half-life mean? It means that after 14 days, you have half remaining of what you started with. Okay, and then you can go another 14 days and you have half of that half, etc. Okay, so we will start with this equation, and then we'll modify it to where we actually do our division of the two. Okay, and so then let's think about what we can plug in. Okay, so what percent do we have in this situation that we can use? Okay, well, they tell us about a half-life, and so that would be using 0.5 as our ratio. Okay. The other thing that they tell us is that we achieve that half when we have 14 days. Okay, so that's the two pieces of information that we can pull from this problem. Okay, so that's why I'm allowed to write 0.5 is equal to e to the 14k. So the 0.5 again is because we have a half-life at 14 days. Okay, so just like we have been doing, this is an exponential, so we need to write it as a logarithm. And so we have the natural log of 1/2 is equal to 14k. And then using our calculator, we can find out what the natural log of a half is, and then we can divide by 14, and we get a negative 0.0495. Okay. Should we be surprised that it's a negative? No, that's what we just talked about, right? It's a growth. Okay. And that's not the actual answer. They want us to write the equation, so all we do is go back and plug in the negative 0.0495 up into the k. Okay, so that bottom line is what they're looking for. Okay. So very similar to what we've done, we just have to look at a ratio instead. Okay. You can also do this with money, like how long does it take to double your money? We just didn't look at it from that point. Okay. Let's go ahead and look at a further application of this. Okay. So we want to know what percent would be left after 30 days. So we are going to actually reason this out before we solve it actually. Okay, so we do want to know what percent would be left after 30 days. One thing I do know is that after 14 days, or at 14 days, there's 50% remaining. Okay. And then if I go another 14 days, I have half of that half remaining. Okay, so at 28 days, I have 25% left. Okay, well, I've only gone 28 days. I need to go 30. Okay, so using the information we have, we know that if I go another 14 days or 42 days, that I would have half of the 25% left, which is 12.5% of the original. Okay, so to summarize that, at 42 days, we would be at 12.5. Okay. Well, the problem asks for 30 days. And so what we know is that our answer has to be in between 25% and 12.5%. Okay, because our 30 days is between the 28 and the 42. Now, we would expect it to be closer to the 25% because we're only 2 days away from 28 days, okay, compared to the 12 days away from the 42. But we should estimate that we are close to 25%, but less, okay, and greater than 12.5. So let's go ahead and do the algebra part of it. Okay. So we go back to that equation that we had found in part 1 or part A, okay, and we are going to go ahead and divide again because we do want to find that percent. And so that is that ratio of our remaining to our original. Okay, and so what we want to do here is just plug in for t. And so we plug in 30 for t because that's what we're interested in. And we use our calculator to take e to the negative 0.0495 times 30, and we should get about 0.23. And so what we know is that we have about 23% of that phosphorus remaining after 30 days. Or in other words, if I started off with 100 grams, then on day 30, I should have about 23 grams of the phosphorus 32 left. Okay. Now, did our estimation, or is our answer reasonable? Okay. Yes, we said it would be between 12.5 and 25%. And much closer to 25 than the 12.5. So definitely a reasonable answer. So let's explore carbon 14 a little bit. Okay, this is the one that's used in carbon dating, if you hear about it. So carbon has a half-life of 5,730 years, so much greater than phosphorus. Okay, we are in years, but it is the same kind of process. Okay, so let's go ahead and find the function for it as well. So again, we took that division and then we used the information that we have. That is, there's 50% or 0.5 of it after 5,730 years. Okay, so it looks like this. And then since it's an exponential, we need to rewrite it as a logarithm. And then we just use our calculator and take the natural log of a half and divide it by 5,730. And we get a very small number, so negative 0.00012, okay, as our decay rate. And hopefully you're not that surprised that it's that much smaller, since compared to phosphorus, I mean, it's a huge difference, right? 5,730 years compared to 14 days. Okay, so our overall function would now look like this. This would enable us to answer questions about how much is left after any certain number of days. Okay. So part B, let's do the same thing. What percent would be left in a bone that's 8,560 years old? So again, I would like us to look at a reasonable answer first. Okay. So we know that after 5,730 years, we would have 50% left. Okay. And so our bone has to be older than 5,730, or sorry, have less percent of 50 than that because it's older than the 5,730. Okay. Now, if I did another 5,730 years, then there would be 25% remaining. Okay. So another 5,730 years is 11,460 years. Okay. And that's when we would have 25%. Okay. Now, our answer should be somewhere in between 50% and 25% because 8,560 is between the 5,730 and the 11,460. So we would expect to see an answer between 25 and 50%. And it should be pretty close to halfway in between those two because I think 8,560, that's about 3,000 away from the 5,730, and it's also about 3,000 away from the 11,460. So somewhere right in, that'd be around 37% would be a reasonable estimate. Okay. So you can do some estimating, but let's go ahead and do the algebra part. Okay, so we take our function that we had found. We divide so that we have a percentage over there. That is what we're looking for. And then all we have to do is plug in for t. And in this case, we're going to plug in the 8,560 years. Yeah. And we end up with 36%. So is our answer reasonable? Yes. Okay. And it does match our estimate that we had come up with. Okay. So that's how you can use these decay functions to date things or just talk about its half-life. Okay. One other thing is, what if we want to go the other way? What if we know how much is left in it? Can we date it? Okay, and that's what they do. And so here we know that we have 22% of its original carbon-14 remaining, and we want to know how old it is. Okay, so we would just go to the equation that we have been using. Okay, we'll just be putting our numbers in different places. Okay, so again, we divide. Now, instead of putting in t, we are putting in the percent that's remaining. So we're going to put in the 0.22 over on the left, and then we solve for t. Now, since t is up in the exponent, we have to solve your exponential equation, and we do that by writing a logarithm. So we have natural log of 0.22 is equal to negative 0.00012 t. Okay. And then just do the procedure in your calculator, divide by negative 0.00012. And we end up with 12,617 years. Okay. And is this reasonable? And if you think about our previous slide, it is, because we had at, what was it, over 11,000 years was 25%. And this is a little bit less than 25%, so it has taken a longer amount of time. And so at 12,617 years, approximately, you have about 22% left. Okay. Now, when they do carbon dating, they do have error attached. They have plus or minus so many years. Okay, but that's a whole different subject. Okay, so no assignment today. Your assignment was the Edpuzzle that you were doing, and next week we'll look at 2 or 3 more applications, and then we will go on to matrices from there. Okay, so if you have any questions, please make sure that you let me know. And one final side note, if you were to do this in another class, they may have you use another formula, and they are related. It's just we're using the exponential form and they may, or we're using the one that has E in it, and you don't necessarily have to do that. Okay, so have a great weekend.